Good morning, friends. Now, the next numerical of exercise 11.18 show that the wavelength of electromagnetic radiation is equal to the de Broglie wavelength of its photon. We know that the wavelength, de Broglie wavelength of photon is lambda is equal to h upon p. Now here we have to prove that this wavelength is same wavelength of electromagnetic radiation. For that purpose, here we consider that the de Broglie wavelength of photon is lambda is equal to h upon p. That is equation 1. Now, momentum of electromagnetic radiation having the frequency f and wavelength lambda dash. The momentum of electromagnetic radiation having frequency f and wavelength lambda dash. This momentum is P is equal to energy of photon upon C, but E is equal to HF upon C. But we know that frequency F is equal to C upon lambda dash. But frequency F is equal to C upon lambda dash. Therefore, momentum of electromagnetic radiation is H upon C. Instead of F, we substitute this value C upon lambda dash. So there is cancelled. Therefore, H upon lambda dash. Therefore, wavelength of electromagnetic radiation is also H upon P. Equation 2. From equation 1 and 2, wavelength of electromagnetic radiation, EM radiation, is equal to the wavelength of de Broglie wavelength of photon. Because in equation 1 and 2, lambda is equal to h upon p, that is the de Broglie wavelength of photon, while here lambda dash is the wavelength of electromagnetic radiation, is also same h upon p. Clear this? Okay. Again, the de Broglie wavelength of photon, we know that lambda is equal to h upon p. Now, the momentum of electromagnetic radiation having frequency f and wavelength is lambda dash. So, from characteristic of photon, P is equal to E upon C. E is the energy of photon, HF upon C. But we know that the relation between the wavelength and frequency, C is equal to F lambda, therefore F is equal to C upon lambda, but here wavelength is lambda dash, therefore F is equal to C upon lambda dash. We substitute here, therefore P is equal to H upon C into value of F, C upon lambda dash. Therefore C cancel, therefore H upon lambda dash, therefore lambda dash is equal to H upon P. From equation 1 and 2, the wavelength of electromagnetic radiation is equal to the de Broglie wavelength of photon. Clear this? Okay. Now next is 11.19. What is the de Broglie wavelength of a nitrogen molecule in air at 300 Kelvin? Assume that the molecule is moving with the root mean square speed of molecules at this speed, this temperature. Atomic mass of nitrogen is given 14.0076 atomic mass unit, and one atomic mass unit is 1.66 into 10 is to minus 27 kg. First, we have to find out the mass of nitrogen atom. Mass of nitrogen atom. M is equal to, here the two atoms, therefore 2 times. Atomic mass is 14.0076 atomic mass unit. And atomic mass unit converted into kg, therefore 1.66 into 10 is to minus 27. So that much kg, it is simplified, so 46.86. 46.86 into 10 is to minus 27 kg. Check it, calculate yourself. Right? After that, the temperature T is given the 300 Kelvin. Boltzmann constant not given, we require 1.38 into 10 is to minus 23 joule per mole into Kelvin. Mole into Kelvin. And Planck's constant H is equal to 6.63 into 10 is to minus 34 joule into 7. Now, average kinetic energy. Average kinetic energy, half m average v square is equal to 3 by 2 kb into t. Right? Therefore, average v square is equal to cancel 3 kbt upon m. Therefore, V average is equal to under root of 3 kbt upon m. We require the de Broglie wavelength. De Broglie wavelength lambda is equal to h upon p. That means we require the momentum of nitrogen atom. Here the speed we obtain V average is equal to under root of 3 kbt upon m. Yes, we multiply both sides by m. So we obtain the momentum. Therefore, momentum of nitrogen atom N2 atom is P is equal to mp. Therefore, under root of here we take the m inside. Therefore, m square 1 times m cancel. Therefore, 3m kbt. 3m kbt. Clear this? Therefore, de Broglie wavelength lambda is equal to h upon t. H upon t. Substitute the value of t. Therefore, h upon under root of 3m kbt. Therefore, h 6.63, 10 is to minus 34 upon under root of 3. Mass of nitrogen atom already we obtained 46.86 into 10 is to minus 27. Boltzmann constant 1.38, 10 is to minus 23 into temperature 300. Thus we obtain the de Broglie wavelength is 0.028 nanometer. That is the de Broglie wavelength of nitrogen atom. So there is the quite complicated numerical. So there is the most important numerical. Again, what is the de Broglie wavelength of nitrogen molecule in A at 300 Kelvin? Assume that the molecule is moving with the root mean square speed of molecules at this temperature. Already we learned about the root mean square value in 11th standard. Atomic mass of nitrogen atom is given 14.0076 atomic mass unit, and one atomic mass unit is equal to the 1.66 into 10 is to minus 27 kg. Now, in nitrogen atom, here the N2, therefore 2 atoms are combined. Therefore, mass of nitrogen atom 2 into atomic mass unit is this, and this is my atomic mass unit in kg. So 46.86 into 10 is to minus 27 kg. Temperature is given 300 Kelvin. Boltzmann constant, Planck's constant. Therefore, average kinetic energy, half m average display is equal to 3 by 2 kb into T. 2 to cancel. Therefore, meaning is m average display is equal to 3 kbt. Therefore, display is equal to 3 kbt upon m. Therefore, average speed of nitrogen atom is under root of 3 kbt upon m. To find out the de Broglie wavelength, momentum is required. Therefore, we multiply both sides by m. Therefore, momentum of nitrogen atom is P is equal to mv. So it's equal to under root of 3 m kbt. Now, de Broglie wavelength, lambda is equal to h upon p. Substitute the value of p. Therefore, h upon 3 m kbt. Now, substitute the value of this constant or the quantity. We obtain the de Broglie wavelength of nitrogen atom is 0.028 nanometer. Clear this? Here the numerical of illustration and exercise are completed. Now, we take some extra numerical asked in past exam of which said board exam and also the theoretical exam. That means in objective portion and also in theoretical portion. Now, first extra numerical, a photon falls freely under gravity of the earth. Its de Broglie wavelength after 10 seconds of its motion. One photon is free falling. Here the initial speed is 0. Free falling under the effect of the gravitational acceleration. After traveling the distance in 10 seconds, first we have to find out what is the speed at here. As we find out the speed, so we can find out the momentum. P is equal to mp. And then the de Broglie wavelength lambda is equal to h upon p. Right? Therefore, from equation of motion, now V is equal to V0 plus GT. Therefore, V is equal to GT. And momentum of photon is P is equal to mv is equal to mg. Here m is the mass of photon. For the proton here we take, therefore de Broglie wavelength lambda is equal to h upon p. At least substitute the value. That means the p is equal to mpgt h upon mpg. T is given 10 seconds. J is the gravitational acceleration 9.8, and mp is the mass of proton. Here we substitute. And h is equal to Planck's constant. So we obtain the 39.6 angstrom. That is the value of de Broglie wavelength. Clear this? Now we are discussing about the extra numerical. These numericals are asked in past exam of board. Right? First extra numerical we just performed. That is asked in 2012 and 15. 2 times that is asked. Either in objective type question or 3 marks or 2 marks question. Now next extra numerical is monochromatic radiation of wavelength 640.2 nanometer from a neon lamp. Irradiates the photosensitive surface of cesium on tungsten. The stopping potential or the stopping voltage is measured to be 0.54 volt. That means here, if the wavelength of light from neon bulb, emitted from neon bulb, is given, there is a lambda 1 is 640.2 nanometer. That means the 640.2 into 10 is to minus 10 meters. At that time, the stopping voltage V01 is obtained 0.54 volt. Right? Now, the source is replaced by an iron source, and its 427.2 nanometer line irradiates the same photocell. Therefore, the wavelength of light emitted by iron is given lambda 2. Lambda 2 is 427.2 nanometer. That means the 427.2 into 10 is to minus 9. Predict the new stopping voltage. We have to find out the V02. What is the value of V02? Right? Planck's constant H, we know that there is the 6.63, 10 is to minus 34 joule into second. And we also require the charge of an electron 1.6, 10 is to minus 19 coulomb. So this data given, we have to find out what is the new potential, new stopping voltage if the wavelength of light is changed. Clear this? Okay. For that purpose, we know the photoelectric equation EV0 is equal to Hc upon lambda. From photoelectric equation, we know that EV0 is equal to Hc upon lambda minus phi 0. Phi 0 is the bias function. Right? Now for lambda 1 and stopping potential V01. So there is a equation 1. Thus EV01 is equal to Hc upon lambda 1 minus phi 0, and we can write EV02 is equal to Hc upon lambda 2 minus phi 0. Now from this equation of photoelectric, if the wavelength is lambda 1, stopping voltage is V01, therefore for lambda 1, EV01 is equal to Hc upon lambda 1 minus phi 0. And because here the photosensitive material is same, wavelength is same, due to the change in wavelength, here the stopping voltage is also going to change. For second wavelength lambda 2, we can write equation 1 in that form. EV02 is equal to Hc upon lambda 2 minus phi 0. Now we take the subtraction, EV02 minus EV01. EV02 minus EV01. So what's upon? Phi 0 is cancelled. Therefore directly we obtain Hc upon lambda 2 minus Hc upon lambda 1. Therefore E is common, V02 minus V01. Here Hc common and this E is taken this side. Therefore 1 upon lambda 2 minus 1 upon lambda 1. Again, from this side E is taken common. So E into V02 minus V01. Right hand side Hc is common, 1 upon lambda 2 minus 1 upon lambda 1. Therefore E is taken on right hand side. Therefore Hc upon E into bracket 1 upon lambda 2 minus 1 upon lambda 1. H is substitute the value of H 6.63 into 10 is to minus 34 joule into second. C, speed of light 3 into 10 is to 8 meter per second. E, charge of an electron 1.6 into 10 is to minus 19. Now into bracket 1 upon value of lambda 2. Lambda 2 is this 427.2 into 10 is to minus 9. Lambda 1 640.2 into 10 is to minus 10 meter. As we simplify, we obtain the potential difference. Therefore, new stopping potential V02 is equal to V01 plus Hc upon E into bracket 1 upon lambda 2 minus 1 upon lambda 1. Therefore, new stopping potential is obtained is 1.51 volt V0. That is the new stopping voltage. Actually, the simplification is quite lengthy. Simplify yourself by substituting the value. Right? Okay. Now, next numerical is an electron is at distance of 10 meter from a charge of 10 coulomb. Its total energy is 15.6 into 10 is to minus 10 joule. Its de Broglie wavelength. Here the 10 coulomb charge Q is placed here. The electron at here. There is a distance of 10 meter. There is a 10 meter distance. So it possesses the total energy is 15.6 into 10 is to minus 10 joule. We have to find out the de Broglie wavelength. Now we know that the equation of de Broglie wavelength, lambda is equal to h upon p. Here we substitute the equation or the value of momentum in terms of kinetic energy. And due to that result, first we have to find out what is the kinetic energy of electron. Therefore, potential energy of an electron is U is equal to minus KQ into bracket E upon R. I is 10 meter, Q is 10 coulomb, and E is the charge of an electron. Here the Q is equal to 10 coulomb, R is equal to 10 meter. H and Planck E, H and E we know that. K is 9 into 10 is to 9 minus sign. Because the potential energy is always negative. Charge 10 coulomb. Charge of an electron 1.16 is to minus 19 upon 10. 10 cancel. Therefore, we obtain the potential energy is minus 14.4 into 10 is to minus 10 joule. And total energy E is given as 15.6 into 10 is to minus 10 joule. Therefore, total energy E is equal to kinetic energy plus potential energy. Therefore, kinetic energy is equal to E minus potential energy. E is given 15.6 into 10 is to minus 10 minus again minus 14.4 into 10 is to minus 10. Therefore, kinetic energy is 30 into 10 is to minus 10 joule. But we know that kinetic energy K is equal to P square upon 2m, mass of an electron. Therefore, momentum P is equal to under root of 2kme. 2km. Calculate this value by substituting the value 2. Kinetic energy is this. Me, mass of an electron, 9.11 into 10 is to minus 31 kg. Therefore, momentum P is equal to 8.97 into 10 is to minus, just a minute. Here directly we substitute this in de Broglie wavelength. Okay. Therefore, de Broglie wavelength lambda is equal to H upon P is equal to H upon under root of 2 km. As we substitute the value, we obtain the de Broglie wavelength is 8.97 into 10 is to minus 15 meter is equal to 8.975. Because the 10 is to minus 15 meter is equal to 1/3. Again here, this numerical is what it says that an electron is at distance 10 meter from the charge q. Electron at here. The distance is r. R is given the 10 meter. So its total energy is given 15.6 into 10 is to minus 10 joule. Now we know that the total energy is equal to kinetic energy plus potential energy. Therefore, the potential energy of an electron is U is equal to minus AQE upon R. So we obtain its value is minus 14.4 into 10 is to minus 10 joule. Total energy given, so we can find out the kinetic energy. Total energy minus potential energy. Kinetic energy is 30 into 10 is to minus 10 joule. Now the relation between the kinetic energy and momentum, K is equal to P square upon 2m. Here for electron is given, therefore here we consider the mass as the mass of an electron. Therefore K is equal to P square upon 2me. Therefore P momentum is equal to under root of 2km. Now de Broglie wavelength lambda is equal to h upon P. Therefore h upon under root of 2km. If we substitute the value of Planck's constant to kinetic energy, already we obtained 30 into 10 is to minus 10, and mass of an electron 9.11 into 10 is to minus 31. And as we simplify, we obtain 8.97 into 10 is to minus 15 meter is equal to 8.975. Clear? Okay. So this extra third numerical is asked in 2013. Now next extra numerical that is asked in 2015. Same as earlier extra numerical 2. Wavelength of the light incident on a photosensitive surface is reduced from 3500 angstrom to 290 nanometer. The change in stopping potential is, in earlier extra second numerical, we had to calculate what is the new stopping voltage. Here we have to find out what are the change in stopping potential. For that purpose, first the initial wavelength that is given, lambda 1 is equal to 3500 angstrom. So it's equal to 3500 into 10 is to minus 10 meter. Stopping potential is V01. Final wavelength lambda 2 is 290 nanometer. Therefore 290 into 10 is to minus 9 meter. And stopping potential is V02. V02. From photoelectric equation. Photoelectric equation. We can write EV0 is equal to Hc upon lambda minus phi 0. Therefore, For lambda 1, EV01 is equal to HC upon lambda 1 minus phi 0. And for lambda 2, EV02 is equal to HC upon lambda 2 minus phi 0. Therefore, EV02 minus EV01 is equal to HC upon lambda 2 minus HC upon lambda 1. Therefore, V02 minus V01 is equal to HC upon E into bracket 1 upon lambda 2 minus 1 upon lambda 1. Clear? The same simplification as earlier in extra second numerical we perform. Now, HC upon E. Here, we take the LCM is lambda 1, lambda 2. Here, lambda 1 minus lambda 2 for Z calculation. So, as we substitute the value of H, Planck's constant 6.63 into 10 is to minus 34. C is the speed of light 3 into 10 is to 8. E is the charge of an electron 1.6 into 10 is to minus 19. And value of lambda 1 and lambda 2. We obtain the change in potential difference is 73.42 into 10 is to minus 2 volt. Or in other words, 0.7334 volt. There is the change in stopping potential. Clear? Again, so generally this type of the long numerical ask, also for long calculation. Right? Again, the initial wavelength is given 3500 angstrom. This wavelength is reduced to 290 nanometer. Therefore, lambda 1, lambda 2 given. We have to find out the change in stopping potential. For that purpose, we assume that when the wavelength is lambda 1, stopping potential is V01. And when the wavelength is lambda 2, stopping potential is V02. Now, we are using the equation of photoelectric effect. EV0 is equal to HC upon lambda minus phi 0. For wavelength lambda 1, we can add this equation. EV01 is equal to HC upon lambda 1 minus phi 0. And for wavelength lambda 2, EV02 is equal to HC upon lambda 2 minus phi 0. Take the subtraction of EV02 minus EV01. So HC upon lambda 2 minus HC upon lambda 1. Left hand side E is common, so E into V02 minus V01. Right hand side HC is common, so 1 upon lambda 2 minus 1 upon lambda 1. Now E is taken on ISS, therefore V02 minus V01 is equal to HC upon E into bracket 1 upon lambda 2 minus 1 upon lambda 1. Therefore HC upon E is equal to, now for bracket, here we take the LCM lambda 1, lambda 2, therefore lambda 1 minus lambda 2. If we substitute the value of these quantities, we obtain the difference in stopping potential V02 minus V01 is 73.42 into 10 is to minus 2 volt, that is 0.734 volt. Clear this?